All right, so now we're going to try to do the impossible. We're going to try to do all of calculus in under 20 minutes. So we have to act really, really fast, go through the whole course. Let's begin. The first two basic issues of calculus, two big questions. What are they? How do you find instantaneous rate of change? How do you find how things are changing instantly? And then, completely separate from that, how do you find areas under curves? Two completely different questions. Turns out answers are completely related. Let's see how they go. Question one, instantaneous rate of change. What are we going to do? Well, what you do there is you first remember, what does rate mean? Well, rate is just change in distance over change in time. It's as easy as that. Distance equals rate times time. Not a big deal. Okay, now what do you do with that? Well, if you graph a function that represents sort of distance against time, then what do you notice? If you want to look at the change in time and the change in distance, what do you got? You actually got a slope of a line, right? This is slope, rise over run. Change in distance over change in time, distance over time. So you got a slope. So automatically we see a really neat thing. We see that the average rate of change between 2 points is equal to the slope of the line connecting them. Well, that's really cool. By the way, what about lines? Maybe you forgot about lines. Want to remind you about lines? Okay, no problem. We can do lines. We can do lines. Lines. Y minus y1 equals m times x minus x1. This is the point slope form. All you need to give me is a point on the line, x1, y1, and a slope, m. You give me those two pieces of information, I can always write down the line uniquely. Always, always, always. Never forget it. Okay, fine. So now we're back to here. Now we can find average rate, and what do we see? Well, in fact, a line that touches the curve at 2 points is sometimes called a secant line. So in fact, we just discovered that the average rate, change in distance over change in time, is equal to the slope of the secant line. Cool. So all you have to do, you want to find average rate, connect the 2 points with a line, find the slope, you got the average rate. No biggie. But that's not what we want. We want instantaneous rate. So how do you do that? Well, what would that be? Well, if I want to find instantaneous rate here, what would I do? I'd make that secant line closer and closer and closer, bring these points together, and look what I'm converging to. I'm coming to a tangent line. Wow! Instantaneous rate of change equals the slope of the tangent line. So we want a slope of tangent line. Well, what's the slope of the tangent line? It's change in y over change in x, change in distance over change in time. But now the change in time from that point to itself is 0. 0 over 0. So I'm getting 0 over 0, which is complete garbage, and that is a big problem. Our first major problem of the course. Okay, so what do? Well, we can that. Distance equals rate times time. We're going to can that. Instantaneous rate of change, I really want that. So what do? Well, how do we get that 0 over 0 problem to go away? The answer is we inch up to it. We just approach the 0 point. And what would that look like? Well, let me remind you what you've done when you were a little teeny kid. When you were a little teeny kid, this is what you were looking at. You were looking at a value of function at a point. Value of function at a point. Okay, not a big deal. There it is. F of a, it's that point. But you don't know anything else about the function. You don't know what's going around there, because all you're looking at is f of a. You open it up, woohoo, the function should be quite interesting. Who knows? Okay, but now what I invite us to do, and what calculus invites us to do, is to look at the function this way. Cover up that point and look at everything else. Open the window, look outside. That's where calculus is. And what you see here is we can see what things are approaching, and we can actually determine the idea of a limit. The limit is what things are approaching. We don't care about what actually happens at that point, only what things are approaching. Armed with the idea of a limit, what can we do? Well, now we can return to the question and figure out, let's take the limit as delta t goes to 0. What do we get? We get 0 over 0. That is called an indeterminate form when you get 0 over 0. So what do? You've got to do some algebraic gymnastics. You've got to factor the top and cancel with the bottom. You can try to multiply by the conjugate. You can try to combine the fractions. There's all these tricks into the trade to actually reduce this to something that you can actually find. So you find the limit. Okay, but once you find the limit and you take the limit as delta t goes to 0, what do you get? You get the answer to the question, how do you find instantaneous rate of change? The answer is what we call the derivative. And what's the derivative? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Looks pretty confusing, doesn't it? It's just rate. It's distance over time, but now I'm letting the time go to 0. Not a big deal. So that's the derivative. Bingo. We're done with the first question. And so now what do we see? Well, we see now that we come back to here, and the derivative, in fact, gives us the slope of the tangent line. Well, that's really cool. If you want to find the slope of a tangent line ever in life, you just take the derivative, and that gives you the slope of the tangent once you evaluate it at the point you want. Great. But for free, we answer the first question. Because remember, the derivative also represents the instantaneous rate of change. So you want to find out how things are changing? No big deal. You take a derivative, plug in, and that will tell you how things are changing at that instant. Okay, great. So now we know all about how to graph these things, how to look at these things, the derivative, instantaneous velocity, boom, boom, boom. We got all out of the way. Now let's take a look at some applications. What can we do with this? Well, how would you take derivatives of complicated functions? Well, if you got a product, you need the product rule. Remember the product rule? Don't memorize the formula, memorize the chant. First times the derivative of the second plus the second times the derivative of the first. So the derivative of a product is this. It's not the product of the derivatives. You got to use the product rule. We've got 5 minutes to spin up here, folks. I got to move faster. What if you have a quotient? Well, then you use the quotient rule. And what's the quotient rule say? If you got a quotient, you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the quotient rule. That's what you use when you have a derivative of a quotient. Okay, great, no problem. Now, what about if you have a really complicated function? What if you got a function that looks like this? It's got insides. It's got guts right in there. So you've got something like this, and you want to take the derivative of that. What do? Well, you got to use the chain rule, folks. This is a thing that you can chain together. There's an inside, there's a blop right here, there's a whole big blop there, and then you've got an outside. So take the derivative of the outside. So the derivative of sine of blop is actually cosine of blop. So it's cosine of blop, and what's the blop? The blop is going to be 3x cubed plus 1, and then you multiply that by the derivative of the inside, and the derivative of that turns out to be just, let's see, 9x squared plus 0. And so there's the derivative using the chain rule. The idea is to peel off like an onion. Just peel off, keep peeling off the outside until you get to the inside. Always remember, though, when you take the derivative, it's if you have sine of blop, the derivative is cosine of the blop. Don't put the derivative in there, put the blop and multiply by the derivative of the inside. That's the key to the chain rule. Now we got the chain rule. Okay, but what about when you have functions that aren't functions? Like what if you have things that are relations? Like x squared plus y squared equals 1, like a circle. How do you differentiate that? How do you find dy dx there? Well, the answer is we use something called implicit differentiation. Implicit differentiation, how does that work? Well, you've got to remember that dy dx, that's an object, that's a noun. And d dx is a verb. It's a commandment. Take the derivative with respect to x. So you differentiate this with respect to x, and what do you see? Well, you see something that looks like this. What you do is you say, okay, I'll take d dx of x squared plus y squared equals 1. The derivative of x squared with respect to x is just 2x, not a big deal. The derivative of y squared, remember how I think about this? I think about this as clumping all this together. And I see this as a blop squared, so I actually use the chain rule, which we just developed, and the chain rule says the derivative of blop squared is 2 blop, and then I multiply that by the derivative of the blop, which is the derivative of y with respect to x. That's called dy dx, folks. The derivative of 1 is 0. And now you can actually solve this for dy dx by bringing this to the other side. That'd be a minus 2x. You divide by the 2y, and you see dy dx equals minus x over y. And there's the answer. So that's implicit differentiation. Just go right through and differentiate implicitly. When you have a relationship, you can still find the derivative. Great! We're making progress here, folks. We are cutting through this stuff. Well, now that you have derivatives, what can you do with that? Well, if you think about it as a velocity, you get instantaneous velocity. If you take the derivative of velocity, you actually get the change in velocity, which is acceleration. So we get acceleration now, we get velocity. Acceleration is just the second derivative of the position. So we can actually take derivatives upon derivatives upon derivatives, as many derivatives as you want. So it's great, we can do that. So higher order derivatives, no problem. What can you use these things for? Okay, we know it's true for velocity. We can use it for velocity. What else can we use it for? Well, it turns out you can use it for linear approximation. Suppose you've got some wacko function. You've got some wacko function like this, woo, and you actually want to figure out the value right here, and you don't know what that value is. But you know nearby there's a point that you can actually compute. So what do? You find the tangent line approximation because you remember that the tangent line closely emulates the activity of the function. Tangent line closely emulates the activity of what the function is doing. So they look the same there. So if you find the equation of the tangent line and then plug in the mysterious point, then you're all set because you can approximate the value by plugging into the tangent line. So how would that look? Well, that's called linear approximation. Here's the formula, but don't bother memorizing it. Just think about it. What you've got to do is you've got to find the equation of the line that's tangent at the known point, which is x here in this case, and this is going to be x plus delta x. The known point plus a little teeny offset is going to be approximately equal to the derivative times the change in x times the function. Plus the function. So that's it. That's the whole thing right there. Linear approximation allows you to actually compute things. Computers actually work this way. Computers know calculus. Everyone knows calculus. You've got to know calculus. Okay, now, what else can you do? Well, suppose that a derivative were to be 0. Well, how could that possibly happen? That could possibly happen because maybe the function goes like this, and I see the tangent over here has slope 0. Or maybe the function goes like this, and I see the tangent has slope 0. In particular, if the tangent equals 0, maybe we have a max or min. Also, maybe the slope or the tangent doesn't exist. Like if we have a wave kind of thing, a cusp, very pretty cusp like the waves. Well, that might be a max, that might be a min. So in particular, you can find out when objects are maximized or minimized. You can find the maxima or the minima very easily by using calculus. What do? You take a derivative and you see where it equals 0 or where the derivative doesn't exist but the function does. Those give you candidates for possible max and min. And what can you use that for? Well, you can do all sorts of now max-min problems. You want to maximize profits, you want to minimize costs. Oh my God, 20 minutes? No, it's only 10 minutes left. They're trying to fool me here, folks, but I'm not going to go up for it. 10 minutes are left. Okay, so you want to maximize cost, you want to minimize cost, you want to maximize profit, you want to maximize area, you want to minimize volume, whatever it is, set up the problem really carefully, figure out exactly what you want to optimize, take the derivative, set it equal to 0, solve, find out where the derivative is undefined, and you've got it made. Really not a big deal. However, you should always remember and never forget the fundamental method of solving problems. So remember how you solve all of life's problems. The first thing you have to do is understand what you're being asked. You can't answer a question that you don't understand. The next thing you do after you understand what you're supposed to find, what you're being asked, is figure out what you know. List every single thing that you know, every single fact. Maybe superfluous, maybe you don't use it, who cares? Write it down, understand it, make it your own. And then the last thing is take the information that you know and see a relationship between that and the thing that you seek. Try to find a connection. Once you got the connection, then you're on the road to actually finding the solution. That is the simple method for finding any single answer to any single problem. Another application, if we think about derivative as a rate, is looking at related rates. Suppose, for example, that you actually have a ladder, for example, that's falling down. The ladder is falling, and you don't want to be sued, but the only thing you do know is how fast the bottom is falling. You want to know how fast the top is falling. What you need to do there is if you know this rate, you can find that rate by linking them up with a connection. In this case, a connection would be the Pythagorean theorem. You can take the derivative with respect to time, because here you see the variable, the thing that's independent, that's always changing, is time. Time keeps on ticking into the future. So you keep going like this, you actually solve this, take the derivative using implicit differentiation, differentiate with respect to time, and plug in what you know how this is changing, and that just tells you how this is changing. Pretty cool. That's called related rates. Suppose, for example, you drop a stone into a very, very still pool. You have a ripple effect. Those make concentric circles that are getting larger. If you know how fast the radius is changing, you can find how fast the area is changing because you have a connection between area and rate. Area equals pi r squared. So there you go, related rates. If you know how one rate is changing, you can find out how a related rate is changing. Okay, what else can you use the derivative for? Well, the other thing you can do is actually graph really, really accurate pictures of functions. Finally, you can figure out that a parabola looks really pretty and bowl-like, like this. And it's not something really exotic, but it's just a nice pretty bowl. How do you do it? Well, you just start taking derivatives and analyzing things. First, you find the critical points. Those are points where the derivative either equals 0 or where the derivative is undefined, but the function is defined. So, for example, in these examples right here, you'll notice that the derivative equals 0 here. The tangent is horizontal right there. The tangent is horizontal here. In this example, the tangent is horizontal here. And then where does the derivative not exist? The derivative doesn't exist here, and the derivative doesn't exist there. Those are candidates for max and min. Those are called critical points. Then what do you do with those things? Well, you set them up on a little number line on the x-axis, and you look at the intervals all around it, and you see whether the derivative is positive or negative. If the derivative is positive, that means slopes are positive, so the function must be increasing. If the derivative is negative, then that means the function must be decreasing. So you can see that the function, for example, here is decreasing, 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 then increasing. Here you can see it's increasing, 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 then decreasing, then increasing. So you can see where it's going up and where it's going down by the sign of the first derivative. That also determines whether you have maxes or mins anywhere, and that's called the first derivative test. Now, how do you figure out the curvature? The curvature is given by the rate of change of the derivative, how the derivative is changing. So what you do there is you take the derivative of the derivative. So you look at the second derivative, and where the second derivative is 0 are potential points of inflection, points where the concavity changes. This is concave up, it's curving upward. This is concave down, this is concave up. So the cup is sitting up, the cup is sitting down, concave down. So here you would see the second derivative is positive, then the second derivative is negative, it changes here, now it's sitting up, it's positive, positive, we're concave up. Here we're concave up, second derivative is positive. Now here we see it's concave down, second derivative is negative, and second derivative here is also negative. This is a cusp point, the derivative doesn't exist there. This is a point of inflection, this is a point of inflection, this is a point of inflection, and that's a minimum. So just by taking derivative and then second derivatives, you can actually figure out and graph a very accurate sketch of even very complicated, almost scary looking functions. By the way, if you've got fractional exponents, expect cusps. That's my warning for the day. Okay, now, if you've got really exotic functions that have denominators, then actually you may have asymptotes. So don't forget that a vertical asymptote is where the function, after you simplify it, the bottom equals 0. So wherever the bottom equals 0, after you simplify and reduce, those are going to give you your vertical asymptotes. Horizontal asymptotes, you take the limit as x goes off to infinity, as you go off to the horizon, and you see what y value you're trying to land to. If you're landing somewhere, then you know you've got a horizontal asymptote, and it's at y equals that value. So So you can put in the asymptotes, and then you can do all the other calculus, get the curvature, see exactly what the beautiful picture looks like. And that was the end of differential calculus. Great, no problem. Now what? Well, now we move on and look at the exact same thing we just did backwards. So we look at Math Jeopardy. Oh my goodness, I have only 5 minutes left. So Math Jeopardy, here we go. So the idea is, if I tell you what the derivative is, how can you find the function whose derivative is that? Well, this is the notion of an antiderivative. So how do you actually find antiderivatives? Well, we saw the formulas for that. If you want to find the antiderivative of x to the n, it would be x to the n plus 1 divided by n plus 1. Take the derivative of that, see you get x to the n. Unless n equals -1, then you're looking at the integral of 1 over x. And what's the integral of 1 over x? Well, it's the natural log of the absolute value of x, because the derivative of natural log we already saw was 1 over x. So great. Now, how can you find exotic integrals? Well, remember that d dx represents differentiating with respect to x, and so therefore the integral with respect to x represents to integrate with respect to x. Now, if you have a very complicated thing there with an inside and outside, you might be able to untangle that, which potentially was made by the chain rule, by using substitution. Let u equal some big blop, and the big blop's derivative should appear somewhere else in your integral. If you've got that, it sounds like a good candidate for u du substitution, and then you've got to change the dx to du by taking derivatives and seeing what du equals in terms of dx. So that's the u du substitution. You got that going on here, and now what you can do, you can take that and look at studies of motion again. Now I can give you acceleration. If you integrate, you get velocity. If you integrate again, you get position. So vertical motion, not a big deal anymore. Lands, no problem. Things moving in space, like this thing here. Watch it, folks. Woo! You can get that. You can anything that moves, anything at all that moves, we can now analyze whether you have crabs or whether you have a bike. It's not a problem anymore, folks. If it's movement, we can anti-differentiate it and figure out what it is. Not a problem. Now, where does this lead us? Well, it brings us back to the very first question of the course, which was, how do you find areas under curves? We have to answer that. We haven't done it yet. It turns out the surprising answer is that it's the fundamental theorem of calculus. And the idea is, if you want to find the area under this curve from A to B, right here, if you want to find that area, then how do you do it? It turns out that if that function is called, let's say, f of x, then all you do is integrate from A to B, f of x dx, because you're summing up little rectangles in here that are base, small change in x, base times height, which is the function. You go from A to B, and this equals f of capital F of B minus capital F of A, where what's capital F? That's the antiderivative. So if you take the derivative of capital F, you actually get little f of x. So just find the antiderivative, plug in the big point, plug in the small point, subtract. That will always give you the area under the curve. You could look at areas of more exotic things. For example, if the thing actually goes like this, then actually, this is actually not very x-easy. The rectangles aren't very clear. The rectangles change from going from green to green, over to green to orange, then to orange to orange. It's not very uniform. However, if you put the rectangles in this way and stack them this way, now you're summing with respect to y. And so here you would actually sum this with respect to y. So you would integrate this dy and put the rectangles in this way, and you put the rectangles in that way and stack. You'd stack from low to high, and you'd stack the rectangles like this. Okay. That is all of calculus. I did it in under 20 minutes. That's what it is. Go back, think about it, have fun with it. Congratulations, folks. You just finished Calculus 1. Have a good time, celebrate. Good luck in the final. Bye.